Have you ever wondered why you are able to rinse mud off your hands with running water only? Or why when you eat something spicy, water doesn't cool your mouth down? Polarity is the driving force behind both of those things and many other things in our everyday life. Dipole movements arise when one atom is more electronegative than the other, causing the more electronegative atom to pull more tightly on the shared pair of electrons. Like in this carbon-fluorine bond, the fluorine will pull more tightly on the electrons, causing a slightly negative charge on the fluorine and a slightly positive charge on the carbon. In order to show dipole movement in a molecule, you draw an arrow pointing towards the more electronegative element with a line towards the more positively charged element. When the electronegativity is equal, like in this bond between two carbons, they will both share electrons equally. There is also no dipole movement in this bond. Polar molecules arise when the dipoles of a molecule do not cancel each other out, like in this water molecule. Because the electron geometry is bent, the dipoles both point towards the oxygen, like so, causing the molecule to be polar. So, in order for a molecule to be polar, the molecule must contain at least one polar bond, like the bonds here between carbon and oxygen in this carbon dioxide molecule. But the electron geometry must also allow for a polar molecule. Because the electron geometry is linear in carbon dioxide, the dipoles will cancel, causing the molecule to be nonpolar. When the surrounding atoms are all the same, these electron geometries will always be symmetric, causing these molecules to be nonpolar. The linear carbon dioxide, as shown previously, trigonal planar, like in this boron hydride, tetrahedral, shown by methane, octahedral, like in this sulfur hexafluoride, and trigonal bipyramidal, like in this phosphorus pentachloride. But if one of the surrounding elements is different, it will cause the molecule to become polar. For example, the molecule with the chemical formula CF3I has a tetrahedral geometry, but because fluorine is much more electronegative than iodine, the pull of electrons will be much greater here on the fluorine side, causing the dipoles not to cancel. In conclusion, in order to have a polar molecule, the molecule must contain at least one polar bond, and the electron geometry must allow for it, in turn keeping the dipoles from canceling each other out.